Have you ever just looked at a giant mountain of data and wondered, how on earth can we boil all of this down to just one number without losing anything important? Well, today we're going to talk about a really powerful idea in statistics that does exactly that. We're talking about the perfect summary. All right, so here's the game plan. We're going to start with a problem that I'm sure you're familiar with: drowning in data. Then we'll introduce this super elegant solution, this perfect summary. We'll see how you can actually test for it, watch it work in the real world, and then, and this is the best part, we'll see how it helps us find the absolute best answer you can possibly get.
Okay, so let's set the stage. In today's world, it feels like we're collecting information at just a mind-boggling rate, right?
Yeah.
Think about it. From every social media post to every scientific experiment, there's just this constant flood of data. It's like we're standing in an ocean of numbers, just trying to find a few drops of actual insight.
And that is the real challenge, isn't it? If you want to know the average height of everyone in a country, do you really need to keep a record of every single person's height forever? Or is there a smarter, more efficient way to do it? This is the exact problem that leads us to a really beautiful solution.
And that solution, that elegant answer to being swamped with data, is what we're calling the perfect summary. Now, the official name for this is a sufficient statistic. All it is a single value, or maybe a couple of values, that holds every last drop of information your data has about the one thing you're trying to measure, what statisticians call a parameter. You know, the best way I've heard this explained is to think of it like a perfect zip file, a lossless compression for your data. You can take this huge, messy spreadsheet, compress it down to this one number, and you lose absolutely nothing of value for the specific question you're trying to answer. It's amazing. So the process is pretty straightforward. You start with all your raw data, right? All the individual points. Then you do a calculation to get your one sufficient statistic. And here's the magic part. You can now literally throw away the original data set, because that single number has everything you need to know about the thing you cared about in the first place.
Okay, but how can we be sure? How do we know that our summary is actually perfect? How do we prove that it's sufficient? Well, lucky for us, there's a test for that. It's called the Fisher-Neyman factorization theorem. And look, I know formulas can look a little intimidating, but don't worry about it. All this equation is saying is that we can take the probability of our data, that's the x, and we can split it perfectly into two distinct parts.
And this slide breaks it down perfectly. The first part is the signal. This is the good stuff. It's the piece of the puzzle that has our summary and everything we need to know about the parameter we're estimating. The second part? That's just noise. It's all the leftover stuff from the original data that tells us absolutely nothing new about our parameter. So if you can neatly separate the signal from the noise, you've just proven your summary is sufficient. Simple as that. Theory is one thing, but let's make this concrete. Let's see how this actually works with a few real-world examples. All right, classic example. Let's say you've measured the heights of 1,000 people. You're assuming heights follow that classic bell curve, the normal distribution, and you want to estimate the true average height for the whole population. So, what's the perfect summary here? It's just the sample mean, the average. Once you calculate the average height of those 1,000 people, you could literally throw away all the individual measurements. That one number, the average, contains every piece of information those 1,000 data points had about the true population average. The rest is just noise. Let's try another one. Imagine a clinical trial for a new drug. Each patient either gets better, that's a success, or they don't. And we want to figure out the drug's true success rate, which we'll call P. So in this case, the sufficient statistic is even simpler. It's just the total number of people who got better. You don't need to know the order of events, like patient 1 was a success, patient 2 was a failure, and so on. Nope. All that matters is the final count. That one number tells you everything you need to know about the drug's effectiveness. Okay, now for a more surprising one. Let's say you're watching something that happens uniformly between 0 and some unknown maximum number. Maybe it's a bus that always arrives between, say, 12 and some unknown latest time. Your job is to guess that latest possible arrival time. Now, what's really wild here is what isn't a good summary. You might think the range of the data, the difference between the earliest and latest bus you saw, would be useful, but it's not. The only thing that actually matters is the single latest time you observed. That one number, the max value, contains all the information there is about that upper boundary. Everything else is totally irrelevant for this particular question. So, okay, we can find these perfect summaries. But what's the big deal? Why do we care so much about this? Well, it's because sufficiency is the crucial first step in finding the best possible estimate you can make.
In this best estimate has a name. It's the MVUE, the minimum variance unbiased estimator. You can think of it as the holy grail of estimation. Unbiased just means that, on average, your guess hits the bullseye. It doesn't consistently guess too high or too low. And minimum variance means it's the most precise estimate you can get. Your guesses are all tightly clustered together. It's the gold standard.
So how do we find this thing? Well, there's a recipe. You start with a sufficient statistic, our perfect summary. Then you check to make sure it's unbiased. And finally, you make sure it's complete, which is really just a technical way of saying there's no fluff, no redundant information. You do those three things, and congratulations, you found the MVUE. And this isn't just some friendly advice, it's a mathematical guarantee. It comes from something called the Riemann-Scheffe theorem. This theorem is what ties all these ideas together. It proves, without a doubt, that if you follow that recipe, if your estimator is unbiased, and it's built from a complete sufficient statistic, then it is, by definition, the absolute best estimator you can possibly create. There's no way to do better.
So, let's wrap this up. This whole idea of sufficiency, it's so much more than just a clever way to save hard drive space. It's really fundamental to doing good statistics. It makes us ask a really important question every single time we summarize data. If this summary I'm making isn't sufficient, what crucial insights, what vital part of the story am I just leaving on the cutting room floor?